All right. Hi, everyone. So I'm going to talk today about, this title is really quite a mouthful. There are different elements in the title that I'd like to focus on one by one. So it's called RichWasm Realizability, Facilitating Specification of ABIs for the WebAssembly platform. So really what I'd like to start off with is by talking about specification of ABIs. Let me start by talking about what is an ABI. Formally, and how would we formally specify one? That's really the goal of this talk, trying to make it easy to formally specify ABIs for mainstream languages. In doing so, I need to tell you about some prior work on rich WebAssembly, RichWasm, which was a paper that appeared at PLDI last year. It's a richly typed IR for safe, fine-grained shared memory interop. On top of the WebAssembly platform. So RichWasm compiles to WASM, as I'll talk about later. And then I want to connect those two threads together and really get to sort of the main point of this, which is that how can we make it easy to specify ABIs for typed high-level languages? Okay, so let's dive in, talk about ABIs first. So just, at a very, very high level, what is an ABI? Well, an ABI, an application binary interface, specifies things like data layouts, calling conventions, things about name mangling, but also additional things perhaps in more richly typed languages, such as safety invariance and ownership and so on. And what are ABIs good for? Well, if you actually have a formal specification of an ABI or even an informal one, you can start thinking about things like, is it okay to link the output of different compilers? You can think about library evolution, like if you migrate a library from one version to another, are you still compatible with the prior clients? And things like language interoperability and foreign function interfaces, you can actually have some hope of showing that a foreign function interface, that its implementation complies with the ABI for a language that you're trying to connect to interoperate with. So let me just sort of focus on a couple of these applications together. So for example, imagine that we have a blue language, I'll just call it a blue language, source language S, and we have two different compilers for it, both compiling to this target. And what we want to know is that even if I compile two pieces of code written, this S1 and S2 written in the same language but compiled with different compilers, I want to know that whether it's okay to link these two together. Do these shapes match, right? And I would be able to do that if I knew that both of those compilers were ABI compliant. Taking another example, suppose that this time I have two different languages, a blue one, a green one. And what I want to do is I want to design some sort of FFI that sits between them. Or somehow support interoperability. I mean, often if you have, let's say, two typed languages, you might still choose to interoperate by dropping down to the level of C, probably CFFI is what you kind of go through. That might be the pink over there. But in a better world, it would be really nice to have direct FFIs between languages and not always have to drop down to C. Especially if both languages are typed and give you nice, strong guarantees, then you'd like to know that, an FFI between them is sort of respects those. So in this sort of situation, suppose that we compile, both of this sort of source code plus whatever FFI stuff I need to do in order to interoperate with the other language. If I compile it down to the target, again, it's an issue of compatibility. Can I really plug these two compiled pieces of code together? Whatever the FFI generated to achieve that compatibility, did it do the right thing? And I'll come back to that. These days, there's actually been a lot of interest in thinking about ABIs, much more than before, I think. For a long, long time, C has been the only language that exports a stable ABI, but there are, in these different language communities, there's been conversation about ABIs. The Swift people have done the most sort of advanced sort of thinking about how can we have a stable ABI, evolve it over time, and still give ourselves the flexibility of being able to sort of change compilers, change libraries, and so on. There's also been work on Krabby in the Rust community, and C++, and in WebAssembly land, there's component model is another sort of look at the same question. So what I want to talk about is how can we provide a formal foundation? I'm interested in verifying compilers and FFIs. Can we provide a formal specification of an ABI? Like, how would we even do that? Because so far, ABIs are all specified in prose, right? And if ABIs are specified in prose, you can't get very far in terms of like trying to verify things. So we're going to talk about a strategy that we've proposed recently in some prior work. for how you might go about formally specifying an ABI. So I'm going to give you like the very, very high level view of this. So basically what we want to be able to do for a source language S, let's say S has a whole bunch of different types, tau, right? Essentially, those types specify an interface on how, about, like that says how you're going to talk to components of this language. That component gets compiled down to the target, and that type gets translated down to a certain shape, a certain data layout, a certain calling convention, right? So what we want to do is basically be able to say for every type in the source language, this type tau, what is the shape of programs that satisfy or the behavior that tau dictates? And so all of the target code, the orange code that I'm sort of putting in the set, I'm advocating that we start building a model of types, source types, as sets of target level terms. And those target level terms that inhabit a type will specify both requirements on data layout at the target level, requirements on calling conventions, and for languages like Rust and so on, you can even bake in requirements on ownership and borrowing, things like that. Okay, so that's the basic idea. We call this semantic typing via realizability. Realizability because basically what I'm saying, what is the target code that realizes the behavior dictated by this source type? Okay, and the term also goes back to a term, realistic realizability that Nick Benton coined back in 2006, where he was using something similar, but there it was to prove type soundness of source languages. So then basically, some target code T is ABI compliant with a source type tau if T belongs to that type tau. That's the basic idea in a nutshell. Okay, I want to quickly show you what these things look like, and I'm going to do that by kind of recapping a paper that we had at UPSLA this year, this past year. And what we did there, just to illustrate that this kind of methodology can be used to specify ABIs, we took a simple functional typed language, but it had a reference counting implementation, okay, which made things kind of pretty tricky. So we give a reference counting, the target was sort of C-ish. We gave a reference counting ABI, and all you need to know for the next couple of slides is that values are boxed and they're reference counted. And we gave a specification for the types, like what is the target code that inhabits the types by using a separation logic. So you'll see little elements of that, and I just want to give you a little feel for what that looks like. So if in the source language you have an expression E that has a type tau under some environment gamma, which is telling us, for all the variables, these variables, X has type TX, then basically what we want to do is we want to turn this syntactic typing into a kind of realizability typing, if you will. I want to say, what is the target code, the orange code, that behaves according to, these source inputs and these target outputs? Or rather, no, sorry, source inputs and source type for results. So basically what we're doing is it's like defining a Hoare triple, where you say, if you give me some memory state, machine state that's sat at the target level, that behaves like the gamma says things should, then after I run E, I get back some target value V that behaves like this result type T. This is a semantic model, also known as a logical relation, if you're familiar with those things. But in a nutshell, I'm going to write this using separation logic. So this says, this is just separating conjunction. This says, I have a vector of all of the inputs that gamma says I should have. So every X with TX, the target level code that behaves like the dictated, the required input type. If you give me all of those inputs that satisfy those input types, then my target code E runs and gives me back a V, and that result will behave like the type T. Right? Okay. So I want to now show you some layouts. So when we construct this model, we end up saying things like this. We end up saying things like, this location L is a reference to an object that behaves like this source type T. Right? And basically all that this is doing is saying that in memory, things look like this. At location L, there will be a reference count stored there. That's just how my compiler is going to do the layout. And at L+1, I will have the object of type T. Okay? This says at L+1, I have some object of type T because it's O of T. Just to zoom in a little bit more, if that type T was just integer, then what the object of type T, you're just saying that at L+1, I have an integer, is expressed as there's some number n such that L plus 1, the memory location L plus 1, contains the number n or points to the number n. Just separation logic used to describe layouts. Just another example, if you have pairs, T1 cross T2, and I want to say at location L, I have an object of type T1 cross T2. Then basically what I want to say is that at L, there is this is the object, right? So at L, I'm going to have the first component of the pair, which lives at L1. And this is a reference to a T1. And at L plus 1, I have a reference to a T2. So at L, I have L1, L plus 1, I have some L2. And those L1 and L2 are references to the T1 and T2. I'm going to give you one more quick one, just to show you, this is idealized. It's not really closures. At the target level, you would have closures, but I've just done functions. This says that at location L, there is a function f such that if you took f and applied it to some input L1, which had a reference to the input type T1, then after you're done running, you'll get back some reference to L2, which is a proper, behaves like a proper reference to T2. And you can do various things using, here in terms of what I've shown you here is a calling convention, which I would call caller retain. And here's something that I would call callee retain. So in this case, the callee, the function itself, retains the reference to T1. So there are variations that are possible in terms of encoding calling conventions, much more sophisticated than the one I've just shown you. And now compiler compliance just turns into this question of, okay, are these two compilers compliant? They are if, given some source code of type tau, if S compiles to T, then T should belong to that interpretation of tau. That's what you need to show for all the code that your compiler compiles. For FFIs, it's similar. So if I have my blue language and I have an ABI for that, then let's say my green language goes ahead and implements an FFI that allows it to talk to the blue language. Well, then I want to make sure that, this component S2 together with whatever bindings the compiler might generate in order to interact with the blue code, that is actually compliant with the blue language's ABI. Okay, so I talked about ABIs. Now I'm going to talk about the grand goal. All right, really, really, really ambitious grand goal. What I'd like to do is be able to support my long-term research agenda is language interop, for those of you who don't know me. What I'd like to be able to do is to support flexible and safe language interop on top of WebAssembly, right? For all the different languages out there, they all compile to Wasm. How can we do better in the future in terms of perhaps designing FFIs between these languages so that we have much more safe interop between typed languages without abandoning any of the type invariants that any one of these different languages might give us? How can we make them interoperate with the other languages when the other languages might not even understand their type invariants? For example, Rust's ownership and borrowing. OCaml doesn't understand that, right? How can we achieve safer interop? So to do that, what we would want is verified safe FFIs. But to verify safe FFIs, as I've kind of been saying, we require ABI specifications. What I want to talk about now is this work that we've done on rich WebAssembly, which is a typed intermediate language. And I want to talk about how RichWasm can help us get to a better future where we can more easily specify ABIs for all of these languages if they compile to rich WebAssembly. Then I'll tie these two things together. So let me talk about RichWasm. So we worked on RichWasm because it was sort of in response to, well, partly safe language interop. We took an example. We said, wouldn't it be nice if we could make ML and Rust or even any language with ownership types safely interoperate? But we wanted to be able to support fine-grained sharing of memory between these languages. And in particular, we gave ourselves this scenario that suppose you have a garbage collected language and a manually managed language. How would you handle that scenario? So I'll get to that in a second. But basically, since Wasm doesn't, memory sharing between WebAssembly modules is sort of all or nothing, right? If I export my memory to you, you can use pointer arithmetic and go read or write anywhere in that memory. So that's not fine-grained, that's terribly coarse-grained. Proposals such as the Wasm component model focus on shared nothing interrupt, but I really like to be able to support fine-grained shared memory interrupt. So RichWasm was designed as a platform for safe interrupt. And in particular, it has a very rich type system with capability types that capture memory ownership and access, fine-grained memory ownership and access. And I'll show you a little bit of the type system in a minute. Okay, so this was sort of the initial motivation. We didn't actually do ML and Rust in their entirety, but what we wanted to be able to support is type preserving compilation from source languages to RichWasm, such that after you've compiled, type checking at the rich WebAssembly level should raise a type error anytime that memory safety for one of the source languages is violated. Now, this requires that you really need to preserve your type invariants. And RichWasm needs to have a type system that's rich enough to capture all of those invariants. You can't have lossy type translations because then you might not have safety. Okay, and then rich WebAssembly is lowered to WebAssembly, which is essentially like mostly type erasure kind of a compiler. Okay, so in actuality, we did core ML and we did a small language with ownership types. We can't handle Rust's immutable borrowing right now, and did a simple FFI on top of that. Okay, and we formalized type standards for RichWasm machine check proofs in Coq. So just want to give you a little bit of a flavor of the rich WebAssembly memory model. So we have these, we have a garbage collected memory and we have a manually managed memory. These are just maps from locations to values, unlike, it's a higher level memory model than Wasm has. They're not byte arrays. We only allow pointers to the beginning of data structures, no pointer arithmetic. So unrestricted memory, linear memory. We call this linear memory because it's linearly typed, because, but it's not linear memory in the sense of just to give you a sense of the type system, we have structured data, variants, structs, arrays, existential types for doing typing of closures. The interesting thing here is that often we keep sizes in the type system. And we need that because we want to be able to do type varying or type changing updates of data stored in memory. So we need to know what the size is, because if you update a field, so this says that there are a bunch of fields of type tau, sequence of fields of type tau, each one of whose size is SZ. And if you want to update anything stored at a certain location in memory, you can always store something of a different type there as long as that type requires less memory, is of a smaller size than what was originally allocated. The main ingredients of this type system are these capability types and pointer types. So you have a pointer to a location L, and you have a capability for location L that tells us what is the type of the contents, what is the type of the data stored at that location, and what are my permissions, read or read write. So this capability is giving certain permissions to a certain shape and size of data. And then we have to distinguish between, capabilities that are talking about the orange linear manually managed memory and the pink unrestricted or garbage collected memory. And in this case, you can see the pointers remain unrestricted, but capabilities to linear memory must always be linear. You can't make copies of them. But if you have a capability to an unrestricted things, for example, an ML reference would have an unrestricted capability because aliasing is allowed in ML. We also have reference types, which you can just think of as a combination of a capability and a pointer, just putting them together. Let's skip over, well, I'll show you this. So sharing memory in rich WebAssembly. So suppose that I have a reference to some location in the stack. Well, this just says, all right, at that location 1, there is an array of I32s. This is pointing to unrestricted memory, hence unr pink. This is the garbage collected memory. And if I want to share it with another module, then I give it that reference. And basically what happens at this point is inside this reference is a capability, and module B will not be able to use pointer arithmetic. It can use pointer arithmetic and go pointer, but it won't ever be able to read or write anywhere else in memory because it only has a capability for this array. When it comes to linear memory, this is the manually managed memory. So if module A wants to share a pointer to this array in linear memory, then it basically has to give up its own access, right? Because only one part of your program can have ownership of linear memory, of some data structure in this manually managed linear memory at a time. Okay. So I'm just going to skip over that. I just want to show you the shape of judgments in RichWasm. Basically, it looks very much like WebAssembly in the sense that you have an instruction list, and it takes inputs on the stack, produces outputs on the stack. But we have a lot more going on in the context because we have more information that we need to track. So we have store typing that will keep track of types for GC'd memory, types for owned memory. Module environment with functions and globals. We have a function environment that keeps a lot more than normal WebAssembly functions. So return types, things to do with polymorphic variables and constraints, because this is a pretty fancy type system, constraints on sizes, for example. But then we also need to thread this like local environment. So we have a environment that tells us the shape of our locals before and after we execute a sequence of instructions, because we allow strong updates, so types might change. So we originally did a progress and preservation proof, okay? And now I want to get to the next point of my talk, where I want to tell you that we no longer wish to do a progress and preservation proof for type soundness. Instead, what we have started doing is working on a realizability model for RichWasm. And again, just to recap from the first part of the talk, what this means is that for every RichWasm type tau, I want to build a realizability model which says, what are the WebAssembly terms? Because RichWasm compiles to WASM, right? So what are the WebAssembly terms that behave like a particular RichWasm type tau? And now this will include things like, it'll be data layout, calling conventions, etc., but also things about ownership, because we have capability types in this type system, right? So building a model of RichWasm types has sets of WebAssembly terms. The model describes all these things, but beyond data layout and calling conventions, also memory ownership and the access constraints that the RichWasm type system has the ability to talk about. What we're doing, and I think Maxime talked about this earlier in the day when he was talking about RichWasm. So we're collaborating with Maxime and Lars, and we're developing a model of RichWasm on top of RichWasm. Basically, when we're done, this will be a specification for the RichWasm ABI on top of the WebAssembly platform. And by the way, when we specify ABIs, we do it once per platform, right? An ABI for a language is really a family of ABIs, one for every single platform. So we're just doing this, right, for the all right, now here's the punchline. Once you have so the goal for, like, why did we design RichWasm? We wanted to be able to do type preserving compilation down to the RichWasm level. And originally it was, safe interrupt. How can we turn unsafe interrupt between source language components into type errors at the RichWasm level? But if you are developing a type preserving compiler from any one of these source languages to RichWasm, then part of that effort is giving, not just compiling, but also showing how the types are going to be translated. So if you have a compiler from ML to RichWasm, you are taking every ML type and saying what its type translation will be. I'm using plus for translation. How to translate it into a RichWasm type, the purple type, okay? But now in addition, since we have a model, a realizability model, or hope to soon have a complete model for RichWasm, what you can do is you can basically, on top of RichWasm, you have developed a type preserving compiler that you have a type translation. If you go look up the meaning of this type, which is your translation, and you go and look up what are the set of WASM terms that inhabit this type and therefore this type, you basically get a specification of the ABI for your pink language. This set of WebAssembly terms, transitively speaking, is the set of terms that inhabits all of those pink language types. So if we do this for ML, we get an ABI for ML. If we do this for Rust, all we need to do is build a type preserving, have the ability to build a type preserving compiler from Rust into RichWasm. That is that RichWasm has to have a type system that's rich enough to capture all of the Rust type invariants. If you drop information on the floor, then it won't be here, right? But as long as you've managed to capture it all, then you can just sort of go read off of the realizability model and get the ABI for all of the types for your source language. So what I'm trying to say is that this is a way, once you do the real work here from RichWasm to WASM, which is really not that hard. hard because these two languages are so close. You pair that up with just type preserving compilation, type translations to RichWasm, and you have a way of specifying ABIs for high level languages without doing the sort of raw crazy work of, oh, I'm going to take this language for every type in this language, I'm going to say what WebAssembly terms inhabit it. That's too many passes of the compiler down, right? That would be really hard to even think about. So this makes that easy. At least that's the hope or the vision. I'll show you just one little element of the realizability model. I have more definitions here, but I had a feeling I was going to skip over them. So I just want to show you, like, if I want to give this HV stands for heap value. And what I'm trying to say here is give an interpretation to my struct type in rich WebAssembly. Struct has n fields. And what I want to say is that this sequence of bytes, which is WebAssembly bytes, does it inhabit, I should have made this purple, does it inhabit this RichWasm term? Okay, so what do? We say, well, there are n fields, so there better be n bytes, b1 through bn, and each one of them has their own sizes because these guys have their own sizes. Each field of the struct has its own size. So there exists this sequence of bytes followed by some extra junk. Why extra junk? Because maybe there wasn't a struct stored there originally, and I had something much larger stored there, and then I decided to store a smaller struct. So we may be in a situation where there's some extra junk. Okay, so if I take all of this, and that is my B star, right? That's the thing, the sequence of bytes that I'm trying to check satisfies this struct type. Then what needs to happen is if I read is just converting every single one of these, BIs, which are the bytes that live in each field of the struct. If I convert them to values, then that value satisfies the type of the tau I, which is the type of the field of that struct. Okay. And this is a star, meaning a big conjunction, separating conjunction. Do it for all the values. Okay, I'm just going to skip over every other stuff, but you can do this for variants. You can then do this for non-heap value types. You can do it for the full high-level semantic typing, which I will just put there for intimidation purposes, I think. Just to kind of say what we're doing with all of this right now, while we're working on the realizability model, we already have a type preserving compiler from core ML to RichWasm, so we have the type translation. In progress is the realizability model using RichWasm. And then the challenge, the thing that we haven't quite tackled yet, but we have to do in order to complete the realizability model is really formalize how the garbage collector is working at the WebAssembly level, because that will be part of the realizability model for RichWasm, right? You have to say, what is the target code that inhabits these types? Okay, so that picture is the takeaway. Hopefully getting to a world where we can more easily specify ABIs for high-level languages. Of course, this is a very long-term project. And as I said, part of our future work for RichWasm, so beyond this picture is just adding features to RichWasm slowly. So for example, the original work just deals with WASM 1.0, but we'd like to be able to add, support for WASM FX, eventually concurrency, and so on. So slowly growing this platform on top of the additional proposals that we developed for WebAssembly so that we can handle more and more features of more source languages. All right, happy to take questions.
So this makes sense. You have this sort of very rich language whose type system encapsulates all of these source languages. What happens if I come along with a new language that has some fancy new typing feature, or if I just take, say, conc?
Yes.
Try and
yes. Add another one, right? A dependently typed.
Yeah.
Right. Okay. So the dependent typing is very hard. So I'm going to leave that one aside. But I would say that we currently are in a situation where, yes, we are slowly growing RichWasm already to handle the languages here. We can't do them all right now. Right now, we can do ownership types. We can do functional language that's GC'd. We can't do all of Rust. So that's also on the agenda. That's the next item past the realizability model, perhaps, because what we can't handle is immutable borrows. The type system at the RichWasm level isn't rich enough. We may need some notion of fractions in order to capture that. But also we don't want to bake in just Rust's borrowing into RichWasm. So at the same time as sort of looking at Rust, compiling, like what is the right set of type features that you want to add to RichWasm so that you could take System Z languages, different ones, not just Rust, even though everyone mostly cares about Rust right now. Right, there's Verona out of MSR. They're a very System Z language. They care about concurrency, but they have a very different model of regions and so on that they use to reason about memory safety in their type system. I've sort of set a goal for us to say, okay, suppose you have Rust and you have Verona, and then there might be others, but like, can we come up with a type system extension for the RichWasm level that kind of unifies the two? That would be really cool. I think that would give us a lot of confidence that we're extending this type system with the right set of features that have the ability to encode different forms of resource reasoning that might exist in type systems at the source level.
Could you perhaps make RichWasm itself extensible?
That is actually another thought. I'm trying to do that on top of LLVM, but not in this project. Yeah. On Zoom? Yeah.
You need to call out the name.
Ben?
Actually, I think Amanyoa was first.
Okay, right, there's an order.
So one question remains: is this concept? Is it in which stage the project is now? Is it in the concept stage, bring new concepts in it so you can formalize it and then implement all these FFI tooling like Uni FFI, for example, from Mozilla? Or is it now in the more later stages?
So basically what we had at PLDI last year, what we referred to as WASM 1.0, or sorry, RichWasm 1.0, is basically a language whose type system is rich enough to handle a GC language, a manually managed language, along with ownership types in source languages. It needs to be grown quite a lot to capture something like, the set of features that are on this slide. I mean, we'd be able to handle Java just fine. That wouldn't be a problem. But as I said, Rust's immutable borrowing we can't handle, and Swift has some funky features as well with borrowing and stuff that we don't know that we can handle yet. Okay, so that's the RichWasm thing. But you're sort of asking, concept stage or not. So again, in the PLDI.
I mean, if I go to Google and search RichWasm, I find a group, a GitHub project which is more or less half dead, and so I don't know where I can find more stuff about it and reference implementations.
Yeah, we don't. I mean, we have a COP mechanization for RichWasm where we mechanize the entire type soundness proof, but we certainly don't have the realizability model for RichWasm to WebAssembly done yet. So I would say it is more in the concept stage at this point. Yes. And the type system can handle certain things, but not many others. But we do have compilers, like sort of a very core OCaml and a small language with ownership types to RichWasm.
Okay, I'm awaiting some kind of implementation in the next years, I guess.
Yeah, I mean,
but it's really interesting.
Yeah,
it's really interesting.
There's a prototype compiler from RichWasm to Wasm as well, but again, these are not, full-fledged.
Yeah, but it needs some kind of libraries for languages anyway. You can so.
And then there's a lot more work to be done in terms of designing FFIs, perhaps, right? So I would say that we're in the very early stages.
Okay, thank you very much. I yield to Benjamin.
We probably only have time for Ben's talk or questions, so after that we can take questions offline.
Ben.
Thanks for your talk. I was wondering, does this extend to machine ABIs, registers, TLS, things like that?
Right now, we're just focusing on giving ABIs at the WebAssembly level and nothing further. If you wanted to do that, you would have to go further down. I'll be honest, doing research at the level of specifying ABIs at a really, really low level becomes really difficult. It's difficult to even fit into one paper, usually when you do that. So what I've liked about targeting the Wasm platform is that it's higher level. Gives us a bit of, allows us to show that you can do really interesting things when, in terms of like preserving rich properties, but we don't have to talk about really low level things just yet. But I think that is totally feasible. It's just that it's going to be a tremendous amount of work. Low level work.
Thanks. But what about us engine people?
Yes. Something more?
No, I think this is great work. I would really like to see if there are some machine level details that make it out of this.
I'd love to collaborate to work on that stuff.
Yeah, I would love to as well. Maybe we can talk offline.
Yeah, that'd be great.